audible.
Okay, thanks for the feedback. Yep. Maybe we wait for a couple more minutes for others to join, or how do you prefer it?
We can wait. We can wait.
A very warm good evening to all. Today, we have gathered here to attend the webinar Embedded Linux and Security conducted by the Student Association of Department of Computer Application, SMART, St. Kitts Sensi Association of Radiant Talents. Let us begin the section with a silent prayer. A very warm good evening to all. Today, we have gathered here to attend the webinar Embedded Linux and Security conducted by the Student Association of Department of Computer Application, SMART. Let me invite St. Sensi Association of Radiant S2MCA to welcome you the section and introduce the resource person.
Greetings to one and all. It gives me immense warmth and great pleasure to grace all of your presence in the interest of the entire committee. Without further ado, let me get into the show bestowed upon me. Being an St. Kitts alumni, this man started his career as firmware developer for Nuclear Instrumentation System at Control Technology, Bangalore in 2009. He was key firmware developer for safety critical reactor coolant monitoring systems such as discrete and continuous level probes and sodium aerosol detectors for India's first ever PFBR. Later, he worked with KPIT Cummins India Limited for nearly a year as senior automotive software engineer, where he was part of the AutoSer team for developing various device drivers and diagnostics modules, mainly for BMW luxury vehicles. He was employed with Robert Bose Engineering India Limited between 2013 to 2018 as automotive embedded software specialist. During this period, he was nominated for a company-funded work-integrated dual master's program in collaboration with State University of New York, USA, and Amrita Vishnu Vidyapeetham in automotive and embedded systems and graduated in 2017. He had also published a paper in customizing Open AVP Ethernet stack for automotive infotainment systems. He is currently employed with Volkswagen Infotainment GmbH, Germany, starting from May 2018 as embedded software engineer, taking care of various aspects of automotive cybersecurity. He is currently pursuing a company-sponsored off-campus master's degree in cybersecurity from RUB, Germany. He is also a German patent in the area of security of interprocessor clock synchronization. With much respect, I'd like to extend a warm welcome to our guest of honor, Mr. Rijo Varghese, who will be speaking later this evening. I also welcome our beloved Mini-Ma'am, our respected HOD Rajesh sir, all students and SMART Executive Committee members to the webinar.
Thank you, Ms. Yeah, go ahead, please.
Let's move on to the actual session led by Mr. Rijo Varghese. It's over to you, sir.
Thank you, Ms. Ahila and Anima Lal, for the generous introduction, I would say. Thank you. And I will take the screen. I will present my screen. Hope it's already visible, or can you see my screen already?
No, sir, it's just coming only.
Okay. Hope it's visible.
Yes, sir.
Yes, sir.
Sir.
Okay, so I have the agenda like this. Firstly, I'll give you an introduction to embedded systems, Linux and security principles. Then I will present a recorded session from one of my previous sessions, partly for my, partially for official purposes. I have recorded it. I have taken out the office-related parts, and I have made it quite general so that I can present it to you. So I'll present the record session, and I'll also try to demonstrate the bootloader and kernel security configuration that we can do while we customize the operating system for an embedded board. And I hope we will have sufficient time for a Q&A and also an interaction session towards the end. So this is how I have structured the session. And embedded systems in general. Many of you might already know what embedded systems are. It is so much of a pervasive technology. It is touching all the aspects of our life, starting from the medical electronics, mobile and wearable devices, automotive, avionics, and you name it. There aren't any fields which the technology or embedded systems have not penetrated into. So it's such a pervasive technology that we see. And one of the characteristics as we see with embedded systems are few of the characteristics, I would say. One would be limited computing and memory resources. This is more of a historic thing, I would say, because in the recent past, things have started changing because of ever increasing performance of CPUs. So this division between microcontroller and a full-fledged microprocessor is actually diminishing and vanishing. So it's kind of merging now, because we have microcontrollers which are almost as fast as a low-end microprocessor. So this difference is actually diminishing in the recent past. And also, other one is that the real-time capability that we are looking for. For example, automotive or avionic control systems, we are looking for a responsive system. What I mean is you have an input from the external world and you have a decision to make. And you would attribute a certain period of time within which the device should take a decision and activate maybe an actuator or take a decision basically. So this is also another important aspect when we talk about embedded systems. So in these lines, embedded systems are a part from general purpose computing, and most of the time we have limited resources to consume. So all these aspects make embedded systems a little bit, I would say, esoteric and special. So that is a very quick introduction to embedded systems. It's a quite a huge field. So yeah, in a nutshell, this is what I could tell you. And Linux, as we might, most of us might be aware, is an open source operating system released by Linus Torvalds, that legendary man. And it's a monolithic kernel. I would tell you what a monolithic kernel towards the mid of the session. And it's used almost everywhere, I would say. General purpose PCs, servers, mobile phones, wearable devices like watches, or whatever. To find to any field of computation that is imaginable, we could find out. We wouldn't be able to find out a field where Linux hasn't penetrated into. For example, the smartphones, the Android. Android is nothing but, deep inside Android is nothing but Linux. So it is basically the Linux kernel with something on top of it. That's all. So, and I would also like to tell you, embedded Linux, when we say that word, we think that it's a different thing, different animal, but it's not. Embedded, there is nothing called there is no version or a flavor of Linux which is called embedded Linux, or maybe there are some esoteric things, but when we say embedded Linux, we are talking about customizing the general mainline kernel for embedded devices. So there is nothing like embedded Linux per se. So you can find the releases under kernel.org. This is the place where you can find the official releases, and we'll come to that later. So security. So these are we saw embedded systems, Linux, and then security. Security. We mostly deal with these three, and sometimes plus one more parameter to say what do we mean when we say security in terms of cybersecurity. So confidentiality, integrity, and availability, and non-repudiation. CIA plus non-repudiation. So confidentiality, I need to send some data to you, and I don't want anybody else to see the data except you. So the means in which we make the data obscure to the intended recipients, only to the intended recipients, not to the other persons. That's what confidentiality is. We don't want anybody else to see the data. So that is one thing. Integrity is, I'm sending you some data, and you would want to make sure that the data that I have. Yeah.
Sir, can I ask one question? Is Ubuntu good for embedded systems?
I would like to take this towards the end of the session, actually. So I would definitely address this question, but I will answer this towards the end of the session. Is that okay with you?
Yes, sir. Yes, sir. It's okay. Yeah.
Okay.
Yes.
Yeah. Thank you. So integrity. When it comes to integrity, I have sent you some data, and you would want to make sure that the data that I have sent is not tampered with or corrupted in the transit. So there you need some sort of a cryptographic mechanism to make sure that the data is not corrupted. So ensuring this is called integrity. And availability is when you try to access a server, and that server should be available all the time. Maybe there is, because of a power failure, the server is going down. That is understandable, but there shouldn't be some malicious attackers who would take down the server with some denial of service attacks, and it's not becoming available to you. So this is availability. Non-repudiation is a little bit more trickier. It's like I have, let's say I have bought a car from Ford. Okay, let me not use Volkswagen because that's my employer. So let me say that I have bought a car from Ford, and once I received the car, I think that the car I didn't like the car the way it is. I didn't do good research before I bought it. But when I actually received it, I changed my mind and saying that, no, I don't like this car. Maybe I'll buy another one. And then I send the car back to Ford, and Ford says, you have issued this purchase request, and that's how you got the car. And then I say, no, I didn't issue this request. Somebody else did. So to take back this car, and then it goes to the court to the attorneys, to the lawyers, and to the judge. And then there should be some means for the judge or for a third party to say that this person actually has sent this request. I shouldn't be able to deny something which I have done. So this is a bit more trickier than other three, but this is non-repudiation is to make sure that somebody would deny the fact that he had done something, basically in a very vague sense. So that is what non-repudiation is. So this is the threats that we might have if this desired properties. These are the properties which we have discussed, and these are the threats we might have if these properties are not, these desired properties are not taken care of, like spoofing, tampering. I could only give you a pointer to what you could learn. So we have only limited time, and we are covering a very, very vast topic. So I could give you these pointers, and you could read it later on and understand what exactly all this means. So spoofing, tampering. Spoofing is something like pretending as somebody else and doing some malicious things. And tampering is actually corrupting the data. Repudiation, we just talked about repudiation, denying the fact that you have done something right or wrong. And information disclosure is that you get data from somebody and you publish it on internet. Think of WikiLeaks or something like that. So denial of service is overloading a server or a resource with consecutive requests, and then it's not becoming available to the legitimate users actually. So that is one thing. And elevation of privilege is you don't have an administrative privilege for certain resource, and you request for a resource, and you find some tricky ways to elevate your privileges to admin or something like that. So these are the threats you might face if you don't address this actually to ensure this basically. So the strike model, I think that's it. And I would also like to tell you one thing. I would be recording this session for legal purposes. So yeah, just in case you object to that, please let me know. So we will directly go to the video, I guess. I would interrupt. I mean, I will stop it in between and clarify wherever things are. I mean, wherever clarification is needed, or you could save the questions for later, and you could write it somewhere, and you could definitely ask towards the end. So yeah, because of the time constraint, unfortunately, yeah, we have to follow this. So yeah, please let me know if you have the audio clearly from this video. Is it audible to you? What comes from the video?
No,
No,
sir.
sir.
No,
No,
sir.
sir.
Okay, then let me share. I mean, I should stop the presentation, and maybe I should do something here. Tab.
Sorry, I think so. The presentation tab, in the presentation tab, we should unmute it. I think so. Another tab will be coming when you present the screen.
Yeah, let me check that.
In which mainline Linux kernel.
Did you hear something?
Now it's audible, sir.
Yes, sir.
Okay.
This session introduces the methods in which mainline Linux kernel.
Are you still not able to hear? Or
We can hear,
No,
sir.
sir, it's audible.
okay, nice. Okay.
Can be customized for an embedded board without using the frameworks such as Yocto or Buildroot.
I will, because this is actually made for a different audience, I would tell you what Yocto or Buildroot is. There are frameworks available with which you can automate the whole process of building a kernel and bootloader and root file system for an embedded board or embedded system. So that is one easy way, but you will not understand much of the things what are going in the background. So under the hood, what's happening, you wouldn't know. So this is an approach that we will see now without using any such automated tools. Yeah, we would customize the Linux. So just as a preamble. So
This session would also include high-level details on the tools that are used and also the software packages which are needed, and also the mention of the hardware that we are using and its connection to the development PC.
We are using a development board from Atmel. This is basically an ARM Cortex A5 based board. It actually houses the SoC SAMA5D36. As we see here, it comes as a full-blown development board, which includes the connectivity options such as USB and Ethernet, and also there are options to expand the board with different capes. If we are to look at the specification or the features of this board, we see that it is housing a processor or an SoC based on A5, Cortex A5 of ARM Cortex A5 processor, and SAMA5D3 is actually an SoC of which the heart is Cortex A5 processor, and there is inbuilt NAND flash, and also there is a 1 GB DDR2. There are different connectivity options as we see here, and also it provides a slot for an SD card, for any SD card based booting or development options. Power can either be supplied directly via a power jack, or it would also run from the power provider using a USB connector. So this is again the overview of the board. So it also has a JTAG connector, which we are not using. This is how the board is designed. At the heart of it, we have this Cortex A5 processor-based SoC, different connectivity options that we have, including JTAG, and different expansion headers, and also the option to connect LCD, SD card, and much more. The board is connected to the PC as follows. Let's say this is our board. We would use the USB, Ethernet, serial, and SD. So let's say this is our development machine, called PC. So the USB is connected, primarily serving the purpose as a power source for the board. Ethernet interface serves as the network interface, and it's crucial when we need to boot the board from the binary which is kept in the PC initially via a network boot via TFTP. So this primarily serves as a network channel for booting from TFTP interface. Serial is for controlling mainly the U-boot prompt and also taking the shell. We would reserve the SD card interface to be used towards the end, where we would finally keep the executables or binaries in the SD and boot the board standalone. There are various options in which a board from power on can be booted until the operating system is given control, and that's primarily dictated by the CPU architecture and also the board architecture. In this particular case, the SAMA 5D36 SoC comes with a ROM boot option where the initial boot instructions are stored in the ROM itself. In the event of power on, these instructions would get executed. What it actually does is it would search for the valid bootstraps, for example, in the NAND flash or in the SD card. And if it finds one, then that would get loaded and then given control. We are using U-boot as the bootloader, which is a popular bootloader available across almost all the architectures. And when we compile U-boot for our board, there is an option to split the bootloading into 2 stages. The first stage being the primary bootloader, and the second stage is, of course, the secondary bootloading. So the ROM boot loads the primary bootloader. It also initializes the DRAM, NAND or SPI flash, and then the U-boot is loaded to the DRAM and U-boot is given control. U-boot actually runs from the DRAM. It initializes the hardware devices. It loads the kernel and also it starts it. It also provides a shell support so that the loading and the execution of Linux kernel can be controlled from the shell itself. Once the Linux kernel takes control, there exists no more bootloader. The whole space is wiped off, and the Linux kernel starts executing the user apps and also the kernel modules which are available in the root file system. The U-boot bootloader sources are already downloaded from GitHub to the PC. Since the target architecture for the board on which we are planning to run the binary is different from the architecture of the PC, we need to cross-compile it. There are basically 4 steps involved before we are successfully be able to compile the sources. The first one being selection of the architecture. Since SAMA 5D36 is an ARM-based processor, we need to specify that. As the second step, we specify the tool chain for the cross-compilation. As the third step, the default configuration for the board for which we are building needs to be specified. We are going to use the NAND flash for storing the U-boot binaries. So we would choose the proper default configuration for the usage of the NAND flash. Now the default configuration is written. Now we are free to change the configuration parameters if we wish to. That can be done by executing the make together with xconfig. So now we have a GUI-based configuration parameter editor. We are free to choose or change the configuration parameters of our choice. Now,
just one point to add here. Just now we have seen the GUI-based configuration parameter editor for U-boot. I didn't mention security here, but there is an option there, or there is a possibility for searching security-related options and changing it. I have made a small or I have opened 2 terminals, and I already have this configuration parameter editors open. Towards the end, I'll show you how exactly you can pick the security-related parameters and make changes there, just to add that point. So let's go back to the video again.
We will leave everything as it is without making any changes. As the final step, we could compile the sources. As we see here, the compilation was successful and the binaries are generated. Now that the bootloader binaries are created, we are ready to flash the binaries onto the board. This figure shows the memory mapping for the CMA5T3 SoC. As we see here, the boot memory is located at the beginning of the memory map. So we would need to flash them here. We would flash the first stage of U-boot bootloader at the 0th location in the NAND flash. And we would flash the second stage or the secondary bootloader at the decimal 40,000. Since we have the bootloader cross-compiled, at this point we can actually flash them onto the board. HML provides a multi-purpose utility called Samba, through which we could flash the bootloader onto the NAND flash. Now we would establish a connection with the board. As we see here, the board is now connected to the Samba utility. This tool is quite useful when we need to inspect the memory or modify the memory or to check of a peripheral register status. Since we are going to flash the binary onto the NAND flash, we go to the NAND flash page first. The NAND flash is enabled. Now the first stage of the bootloader is chosen to be flashed. And the file is written now. The same step goes for the second stage of bootloader as well. The second stage of bootloader needs to be written to the address hexadecimal 40,000. And it is also worth mentioning that this address needs to be specified when the bootloader is compiled. This is actually hard-coded in the configuration itself, so that the first bootloader or the first stage of bootloader, U-boot SPL, would know where the secondary stage of the bootloader is, and the binary needs to be returned. So at this moment, we have the bootloaders being the first and the second stages being written to the NAND flash in the respective locations. We could exit the tool now. Now the bootloader is flashed, and we could reset the board and see if we could get the U-boot prompt. We could use a Linux utility called PicoCom, which is similar to PuTTY. It uses the serial connection with the board through which the U-boot prompt can be accessed. PicoCom is already installed. Now the board is reset. As we see here, now the board has booted with the bootloader that is flashed. Since there is no Linux kernel or root file system present, it would by default drop to the boot command prompt. The uboot prompt is useful when we need to customize the Linux booting process, which we will see later when we actually compile the kernel sources and boot it. Now we can finally compile the kernel sources that is downloaded from the mainline Linux distribution from kernel.org, which is already been downloaded to this PC. And we would also need to follow the same steps that we have followed for compiling the uboot bootloader as well. So those steps being setting the architecture. In our case, this is still ARM. We also need to choose the cross-compiler toolchain. As the next step, we need to choose the default configuration for the board or for the SoC that we are compiling it for. At this point, we can make the changes to the config file for modifying the kernel parameters, configuration parameters for kernel. And as the final step, we can compile the sources. Architecture is specified, and the cross-compiler toolchain is specified, and the default configuration for SMA5 SoC is specified. And as the next step, we could use tools like xconfig or menuconfig to be able to edit the kernel configuration parameters. This is a GUI-based configuration parameter editor, which is quite convenient from other command line based tools such as menuconfig. This is superior in terms of the benefits that it offers, like searching for a configuration parameter, which is not present in the configuration editors like menuconfig. So we could search for example, the security related configuration parameters to see what all we have here. As we see, there are so many security related options. At least the name starts with security. This may not.
One more point to add here. Yeah, the security related configuration parameters in Linux kernel itself is a very vast topic. We have so many options to choose from. There are so many configuration parameters, options to use third-party security features like SELinux or I think it's called AppArmor. So there are so many things in this area. So what I would like to give is only a pointer. It's not complete in the sense that we are offering or I'm offering a complete tutorial or a lecture on the Linux security. No, these are pointers and these are topics worth talking in its own right, actually. Kernel configuration parameters and kernel security modules are very big and vast topics, and they are worth considering as a topics on its own right, actually. So just as a hint. So let's go back.
Not be an extensive or comprehensive list of all the security related options that we have, but it certainly gives a hint on the possibility of making changes to or modifying the security related configuration parameters in the kernel. Like the AppArmor support, SELinux support, using SquashFS. There are so many options to choose from. And at this point, we could leave all the options to their defaults, and we could close it and finally build the kernel. It usually takes 5 to 8 minutes on this PC, depending on how fast the machine is and also how many cores does it have. This compilation time really varies. Now the compilation is over and the binaries are generated. Out of the compilation, we would basically need two artifacts. One is the compressed binary of the kernel itself, and second one is the device tree binary. They are located in the boot folder under the architecture which we are building it for. So it should be under architecture, ARM, boot. So this is the kernel binary. Since Linux is a monolithic kernel, all the sources that are built for the kernel except the loadable kernel modules will be part of the single kernel image that is built.
That's exactly what we mean when we say a kernel is monolithic. There are different types of kernels. Linux is monolithic because of this reason. Whatever you build whatever you build for making an operating system itself will become just one big file. And you will have additional loadable kernel modules, which will definitely, it ends with .ko. The kernel modules will be named with the name, and the extension will be .ko. So these are loadable kernel modules, which will not be part of the final image, kernel image that we make. And also the applications, Linux application, regular Linux applications that we write. Usually it ends with the extension .out. So these are the files which will not be part of the kernel, but whatever we build the kernel into, it will become just one file. So this is one reason why it's called monolithic.
In addition to this, we would also need the compiled device tree or the device tree binary, which can be found under the device tree sources.
I think one addition is needed here also. Device tree, it's a fancy sounding name, but there is nothing much of fancifulness there, I would say, because device tree only describes the hardware structure of a microcontroller or a processor, basically. So what sort of interfaces does it have? What are the properties of those interfaces, and which are the locations, hardware locations these peripherals are located? All this will be written into a special file called device tree source, and that is written using a special language. That's a special language on its own right. It's called hardware description language. So using this, we will write a file, device tree source, and device tree source will go to a special compiler called device tree compiler. Device tree compiler will take this as an input and make the device tree binary. Usually in Linux, it ends with or the extension is usually .dtb. So we are actually looking for DTB here.
The device tree source, which is written in the device tree language, and that's compiled to device tree binary. To compile the device tree source, we need a special compiler called device tree compiler, which is already part of the build toolchain. So device tree source is translated into a device tree binary, and there are other binaries as well for different boards, but we are interested only in the binary that is built for the board that we are building it for. Basically, these two are the artifacts which we would need for booting our board. There are multiple options through which the binaries can be copied onto the board. One being the JTAG. Another option is to use TFTP, through which the binaries on the PC can be exposed to the bootloader that is running on the board. We would go for the second approach. In order to do that, we need a TFTP server running on the machine, which is already been installed. So we would basically copy these two binaries into that folder. And also, it's worth mentioning that the bootloader should support the TFTP based booting. So that should be specified while compiling the bootloader. When we compiled it, we used a configuration where TFTP was enabled. So the device tree and also the kernel image is copied to the TFTP folder, which is exposed as the server. So it should be visible from the board, from the uboot prompt. Now we would power on the board and let the uboot drop to the shell. Since the binaries are exposed in the TFTP server, we could directly load them onto the RAM before we actually write it onto the NAND flash. The kernel image is loaded onto the RAM at the location specified here. Now the device tree is being loaded. Before we actually write the binaries onto the NAND flash, we could actually see if it's booting properly. So boot Z is the uboot command for booting the binaries which are loaded. So at this location, we find the device tree binary, and here is the kernel. So the kernel is given control from the uboot, and it was able to successfully boot, but it stops in between because a root file system was not found, because of which the kernel is panic and the booting is halted. To be able to boot Linux,
I think one more addition is needed here. Root file system is nothing but a directory structure, basically a directory structure where the kernel will look for the essential utilities like init process and the shells. So this is basically one thing Linux would need in addition to having having a memory accessible plain memory accessible, that wouldn't be sufficient for Linux to boot successfully. It would need a proper root file system, an organized structure where it can find the necessary and essential applications and processes.
It also needs access to a root file system, which is not present at the moment. Later, we will see how we could create a root file system and give Linux access to the root file system to be able to boot successfully. In the previous step, we have actually downloaded the binaries onto the RAM and tried executing directly from there. A better approach would be to store these binaries onto the NAND flash so that it can be directly loaded when Linux boots up without relying on the TFTP interface at all. We would revisit the NAND flash organization once again to define the locations in which the device tree binary and the kernel can be stored. The memory area between these two locations is allocated for the environment variables and also its backup. The address starting from this until is allocated for the device tree. And the kernel image is returned starting from this location. We will now use the uboot commands for NAND erase and write to flash the kernel and also the device tree binary onto the NAND flash. In order to do that, we need to take the uboot prompt first. We'll now run the picocom utility first and reset the board. Uboot now has dropped to the prompt. Now we are free to use the NAND commands for erasing and writing the NAND flash. With this command, we specify the location from which the erase should be performed, and this is the number of locations which should be erased. So these locations are being erased for storing the device tree binary. This command would actually wipe the storage for the kernel image. Both were successful. Since the board has been reset, we would still need to copy the binaries from the TFTP server to the RAM so that in the next step, we would be able to write them onto the NAND flash locations which we have wiped already. Now the kernel image has been loaded to the RAM from the TFTP server. And now the device tree binary is also loaded to the locations for the kernel and for the device tree. Of course, they are in the RAM area. Now we could finally write these images onto the NAND flash. Now the device tree is being written. This is the RAM location where it is.
To be able to flash something onto the NAND flash, which is a non-volatile memory location. When we use TFTP, we actually need a temporary placeholder or a scratch pad place where you need to copy it there first. From there, meaning we read it from the TFTP to a volatile memory, which is RAM. From there, we copy it to the NAND flash, which is non-volatile. So first step we already have done, and the second step, we are going to do now.
Loaded from the TFTP server. This is the starting address for the NAND flash. Now the device tree and also the kernel images has been successfully returned to the NAND flash. To be able to execute the Linux kernel, which we have flashed now, we could either load it directly from the uboot command prompt, or the whole process can be automated by adding the boot command or modifying the boot command environment variable. We have seen the first option in the previous case. Now we will modify the environment variable so that the whole booting process can be automated without even making the uboot drop to the shell. To edit the environment variable, the command edit nv is used. And the name of the environment variable is bootcmd. With this command, we specify the locations from where the binaries shall be read.
This is how exactly when we boot up Linux general purpose PC behaves. Basically, the uboot, let's say uboot is used as the bootloader, then the bootloader environment variable would be properly set to point to the kernel sources, kernel binary, device tree, root file system, and all that. So it would know exactly where to fetch all this. Without this information, uboot wouldn't be able to proceed any further, and you will basically drop to a command line where you would need to add or provide these inputs to the bootloader, basically. So this is what actually happens when we boot up a Linux machine.
And finally, the command to execute the binaries which are loaded. The environment variables change needs to be saved. Now we could reset the board. the kernel and also the device tree were successfully read from the NAND flash, and the U-boot has given control to the kernel. Kernel has successfully started executing, but towards the end we see that the kernel went into panic because there was no root file system present, so the booting process is halted. The next step, we would see how a root file system can be created and supplied with the Linux for a successful booting. Root file system is basically the topmost directory, which is often denoted by /, and it is organized as a tree structure which is made of different directories and folders underneath. It should have the mandatory or essential Linux utilities such as init, and it can also contain the custom applications which are compiled for the particular embedded systems to run. The root file system also offers means and space for saving and retrieving data in different file formats. To create root file system, there are a few options. One option is to manually figure out the essential Linux applications which are necessary for a board, download them from the respective repositories, open source repositories, and compile it for the target architecture. This is a time-consuming and tedious process often, and also it is prone to mistakes. A better alternative, especially in the case of embedded Linux applications, is to go for off-the-shelf root file system.
At this point, I would like to get your feedback. Are you still following me, or are you lost? Just let me know if you think it's a little bit it's a little bit hard to grasp or not getting a proper perspective. Let me know. Then we would think of other options to explain things to you. Because it was originally made for a different audience. So please let me know if you still follow it, or do you want me to talk about it and not present it anymore. So let me know, please. Maybe you could raise your hand if you don't follow.
Yes, sir, it's fine. Yeah, you can continue.
Okay, thanks, Melvin. And how about others? If I could get some more feedbacks, that would have been of great help. Otherwise, I would assume that it's okay. You are still following me. We have some 10 more minutes to go. I mean, it goes the same way like this. You have, now we will see how a root file system is being customized and how that is fit, given to the, given control. So yeah, that is how it goes. If you feel a little bit dizzy, let me know at any point. So yeah. Okay, on to the video.
Such as BCBox. BCBox basically offers a basic and essential set of Linux applications and utilities which are necessary. BCBox is already downloaded to this machine, and the compilation process is pretty much similar to the compilation that was done for U-boot or Linux kernel itself. BCBox also offers a configuration option based on menu config utility, where the root file system contents can be customized. There are several options to choose from, including the selection of utilities which are necessary, init utilities, and much more. But for the moment, we can keep everything to their defaults.
Maybe I'll speed it up a little bit. Okay, I'll give you upfront hints what we are doing. So without going further through this video, maybe it is a little bit boring. I mean, it's a little bit boring even for me. So so no worries on that. So basically, BusyBox is one umbrella, I would say, under which all this necessary essential applications like init process and others which are needed are built into a single file, and there are soft links for all of these different soft links are pointing to the same executable finally, and BusyBox is an easy thing. When you need a very lightweight root file system and you don't want to waste a lot of time in customizing and going through each and every constituents that you would actually need. So that is how it goes. So if I go a little bit further, because I think it's a little bit too much for you. So maybe one thing that I would like to tell you is SquashFS. Squash file system is a read-only file system. Let's say you have an application, an embedded system where you wouldn't expect any data modifications in the field. You're giving it away, or you're deploying it in the field, and you expect that there should be no data changed over a period of time. Then a Squash file system is a type of file system, a format of file system, which tells you or which ensure that the data stored within Squash file system cannot be changed. So this is a read-only file system, Squash file system. When we talk about security in embedded systems, we would actually talk about SquashFS, and without talking about SquashFS, it is difficult to go out of the topic actually. So this is one thing which we will do. What we have been doing is actually customizing root file system. And just now I told you Squash file system is one type of file system, and that is exactly what we are customizing it for the embedded system that we are preparing. So root file system, the final root file system is created here, and then we would copy it into an SD card. This is /dev/sdb is an SD card to which we copy the root file system, and the root file system. The copying is happening, and finally we are booting the board. Finally, we are booting the board. We had the first and second stage of bootloader. Then we had the kernel images. We had two of them. I mean, two parts, I would say. The compressed kernel image itself and the device tree binary. And the fifth thing that we have now is actually the root file system. So root file system is also part of the thing. The initial four, what I mean is first and second stage of bootloaders, there are two. And then we had device tree binary and compressed kernel image. All these four, we put it into the NAND flash, which is a non-volatile memory of the SoC board that we have. And the fifth one, which is the root file system, in SquashFS format, we put it into into an SD card, and we plug that SD card in, and basically that's it. I'll show you the board, the actual board, and how to do that look. I'll show you in a while. So at this point, it is actually being booted. some parameters. We need to specify the boot parameter also. And finally, we have come to the end. You see, you have the command prompt. This is any of you have used a Linux machine, you would know there is something called terminal. If you go to terminal, pretty much whatever you do with your GUI, KDE, or whatever based environment, you can do that. It's a bit difficult, but you can do that from the command line as well. This is exactly the command line that you're seeing here. You can execute some commands, which means, you see, PS will list the processes which are running. So the device is actually up. I have given a command here, PS, and command has given so many processes here. If you execute the same command in a Ubuntu or so, you will get a very big list. But this is a small processor. We exactly know what are there. We have customized it. So this is only small that we see here. So yeah, there are some references which I went through while doing this. And I have omitted some details also because it's not so appropriate. It is, something which is not so appropriate for the audience. I have changed it because I'm unable to talk anything about my work or, So I will stop it now. Hope it is clear to you because we have time constraint. And at this point, maybe just one thing I'll show you. I'll stop. I'll present my entire screen, and I'll show you something. This might be of interest to you because if you like security, you might like it. This is for U-boot. This is the configuration. Let's say you want to find out the security related configuration here. I don't know, at this moment it's not working for some reason which I don't know. Some secure address. You see, there are so many things which you should. So these are of topics which are topics on their own right, basically. So there are so many options related to security. These are secure mode by default. So these are hints or pointers which, if you like security in Linux and operating systems in general, you would really like all this. So this is for U-boot configuration, the security parameters. When you go to, let's say, go to kernel configuration. This is actually for kernel. When I search for security, I'll find so many security options. They are vast topics. I wouldn't be able to talk. Not all of them I'm aware of also. So they are very vast and very complex topics. So this is one thing which I have I wanted to show. And I will go back and see how much justice have I done to the agenda that I have set. So general introduction, I presented it, and also I demonstrated a bootloader and kernel security configuration. At least the GUIs I have shown you. And I think at the moment we can move to an interaction session, and I hope I can do justice to it. Stop presenting. If you have, I think one of you had one question on how about using Ubuntu in embedded systems? Basically,
Yes,
basically Ubuntu is just one flavor, I would say, meant to be used in general purpose machines. I wouldn't even say that it's meant to be used on a desktop PC, but it is mostly made customized for general purpose computing environments, not for embedded systems. But if you are really keen, but that wouldn't yield much, but if you're really keen, you can get the Ubuntu sources because it's an open source project. You can get the actual real Ubuntu sources, then run through the menu config or xconfig configuration editors, and you can make a lightweight kernel out of it. But I would tell you that this wouldn't be any different if you do it from a mainline Linux kernel. From kernel.org, because that's what they have taken and they have customized. And now if you take this and customize it back to something else, you can do that, but you wouldn't earn or yield anything from that actually. So it is only a flavor of Linux. So it is, I would say it is not meant for embedded systems. Yeah, hope I have answered you. Yeah. Do you have any more questions? Maybe in the meanwhile, I could show you the board, the actual board. Yeah, this is how it looks like. Yeah, this is a general purpose board. Yeah, quite nice actually. So if you like embedded systems, you can buy something like this. And there are a lot of resources online. You could maybe to have some fun with the such things. This is a bit expensive, but yeah, there are other boards which are quite cheap, like Raspberry Pi or something like that. Yeah. Any more questions? Did you really follow me, or did I just made you dizzy, confused? I don't know.
Hello, sir.
Hello.
Sir, from your experience, could you please share us about the path to be taken for choosing an automotive cybersecurity as a profession?
Yeah, embedded systems is something which I liked because I actually from this electronics and physics background, I liked that path. So even after MCA, I went to this embedded field, and then in my second job became part of automotive software development. I would say, and then I happened to be in security, and then I liked it more and started learning more about it actually. So I would say it is partially accidental. It was not fully planned actually to end up in cybersecurity. It was accidental, and that's all I could say.
Okay, sir.
But this is definitely one nice field, I would say, in the future, because technology is becoming more and more pervasive in all the areas. Like people used to say in the past, oil was the greatest resource. Now data is the new oil. So anybody who would want to do business, they would, the first thing that, at least in the technology, they would need, or even in the business, they would need data, and they are keen to get the data from whatever sources they can get their hands on. So it is data is the key thing now, what drives the market. So when it comes to data, it also opens up a lot of problems, I would say, or challenges, I would say, a better word, because data is most often associated with people and places, and it becomes more personal, and then there is a problem of security and privacy and all that. So in the future, this is going to go up basically. As the technology is becoming more and more part of our lives, security also should cope up with that. For example, we have our mobile phones, we have smartwatches, whatever. So it's all collecting data, and there should be some means of ensuring security and privacy. So this is, I think it's a quite green field in the future. And if any of you like security, please aspire that actually. Yeah. It's a nice field to be, and that's all I can actually suggest to you, I would say.
Hi, sir. I have a question. Sir, could you please brief us on the practical component of cybersecurity? So what I meant is the best programming language that we can apply in this domain or learn to get some career benefits on cybersecurity.
Yes. When we talk about cybersecurity, we don't really specify a language. Certain languages has benefits when it comes to developing a cryptographic algorithm. Let's say, for example, C is known to be a programming language which has the least of. I mean, I wouldn't say least. Of course, assembly is the least, but when it comes to higher level programming language, C really stands out because it offers very less overhead, and the programmer is given the ultimate control of what he's doing actually. So I'm a big fan of C, and I'm working with C for 11 years or 10 years or 11 years now. So C is definitely one good thing that you should definitely have in your basket if you aspire to become a cybersecurity professional. And also, I would say it is better to have some scripting knowledge like Python, Python, Perl, Python or Perl. These scripting languages are of, I mean, I don't know much of them, but definitely that is there in my table to learn more. The scripting languages are nice to have. C++ would probably supersede the C scene now, what the C programming scene that we see in embedded systems now. In security also, things might go in that way. Some cryptographic libraries are written in C++, but most of them are written in C actually because of its performance advantages and benefits that it offers. So if you ask me, I would say C, C++, and some scripting languages like Perl or Python would definitely be of help actually if you aspire to become a cybersecurity professional. Yeah, and it is not just programming security. When we talk about security, it is not just programming. There are other things like hardware security. So it is a vast area. Programming is just only one part of it. I mean, there are multiple facets to it, I would say. Yeah. I hope I have answered you.
Yes, sir. Thank you.
Hi, sir. So I do have a query. Okay, sir. So we are having a theory paper in cybersecurity as per a university curriculum. So if we're adding some practical implementations, whether it will help us to build a automotive, enhances us to have an idea on this automotive cybersecurity, sir? Whether it will be help us to get into that career?
Automotive cybersecurity is not any special, I would say. I mean, when we say automotive cybersecurity, we don't really mean anything special or in other way, I would say any security measures that you would consider when you develop an IoT application, maybe you would consider the same thing when you think of security, when you think of security in automotive also, because it is accessible to people. It is they are able to tamper the devices, because once the car is bought, it is his property and he can do whatever he would like to do. We have seen the Robert Bosch scandal sometime in the past. Some gimmicks that they did in the ECU. So these are basically the things that you would consider. But in general sense, cybersecurity in automotive is not much different, I would say, in comparison with let's say Internet of Things security, because it is accessible. But when you talk about security of a server, it's different, because people of certain administrative privileges would go to the server and do their work there or manage it. Then the security that you're talking about is completely different. But when it goes to a real person and he owns it, and then we have to make sure that there are not much threat. I mean, that is IoT or Internet of Things security. So it is pretty much similar to the IoT security. So yeah, it is not much different from IoT security, I would say. Internet of Things security, if you have heard of IoT. Yeah.
Yeah, thank you, sir.
Hello, sir.
Hi.
Sir, is it true that too much security components and electronics in vehicles kill the enthusiasm in driving?
Okay. Why did you ask that question? I don't know. I mean, yeah. Let me try to answer. When we we basically talk of usable security. That is a topic of its own right, I would say. This is a nice question. That's why I asked you. Why did you ask this question? Because when security experts design things, they usually think of security, not the usability of the things. Actually, let's say when you design an iPhone app or user interface, then you would, as a security professional, you tend to think as a security professional. The usability doesn't come into your perspective, actually, because you are trained in that and your thinking is in that line, actually. But there is something called usable security. When it comes to security, it should not hinder the usability. In your case, in your question's case, that is exactly what it is. It shouldn't kill the enthusiasm or the liking for driving. Actually, it shouldn't make too much of a complication for you to get into the car. Let's say you have to provide your thumb impression and then you have to show your passport. So that's stupid, right? That kind of security is absolutely stupid. If such a security is coming into the users, people will not buy such things, actually. So when we ensure security, we ensure security, the real security, and also we should also ensure the usable security. And somebody should ensure that the system is still usable and still that wow factor is there, or oh, I like this, or that excitement factor is still there with the customers to go after a product, actually. So nice question. Thank you. Yeah.
Thank you, sir.
Any more questions?
I think there are no more questions left.
Okay, then you can go to your valedictory.
Now let us wind up the session. I invite Mr. Adityan S. Nair of S4 Integrated MCA to deliver vote of thanks.
Okay. Good evening, everyone. I am here to present the vote of thanks for today's webinar. I would like to thank our guest speaker, Mr. Rijo Varghese, for visiting and enlightening us with his knowledge. Today's webinar was full of knowledge and interesting things. I am pretty sure the precious knowledge that you gave us will definitely help us in our future. Next, I would like to thank our HOD, Mr. Rajesh KS, for giving us the opportunity to attend such an informative webinar. I would also like to extend our sincere thanks to Professor Mini Punus, Director, MC, and Governing Board members, Engage Group of Institution, for our encouragement throughout the webinar. I would like to thank all the staff for organizing such an informative and interesting session for us. And last but not the least, I would like to thank the students for their cooperation throughout the webinar, which made this a successful one. Thank you.
Thank you, Adityan.
Okay, thank you for giving me this opportunity to talk to you. Being an alumni of St. Kitts, it's a great pleasure for me to be here and talk to you all and have this discussion. So thank you very much, and have a nice evening. See you later sometime. Bye.
Thank you, sir.
Thank you, sir.